Hello everyone. In our previous video, we explored the fundamentals of pile foundations, including their types, benefits, design considerations, installation methods, and real-world applications. Today, we're taking it a step further. In this video, we'll guide you through the design process of a simple pile cap for a concentric column. Along the way, we'll also touch on key code provisions to ensure compliance and clarity. Let's dive in. Now, let's start with a key provision from the NSCP C 101/2015, Section 4.1 3.4.2, which outlines the minimum effective depth requirement for pile caps. It states, the overall depth of the pile cap shall be selected such that the effective depth of the bottom reinforcement is at least 300 millimeters. This guideline can also be tweaked and used to determine the minimum overall thickness of the pile cap. The shape and dimensions of a pile cap are fundamentally determined by the pile layout, which is based on design calculations and the requirements of applicable code provisions. However, some codes, like the CRSI Design Guide for Pile Caps, provide typical pile cap sizes and shapes for various numbers of piles, as illustrated in Figure 4.4. Utilizing these standard layouts offers several advantages. Not only does it streamline the design process by providing efficient and pre-established configurations, but it also enhances constructability. The familiarity of these layouts among contractors ensures ease of implementation and reduces the potential for errors during construction. When designing a pile foundation, it's essential to account for the minimum spacing requirements between piles. These requirements are crucial for several reasons. Firstly, they help avoid pile group interactions, ensuring that the load-bearing capacity and settlement behavior of each pile remain effective. Secondly, for board piles, sufficient spacing facilitates ease of construction by providing room for equipment and preventing interference during installation. Various design codes specify these minimum spacing provisions. For example, both BS8110 and ACI 543R12 recommend a minimum spacing of 3 times the diameter of the pile. Meanwhile, the CRSI Design Guide for Pile Caps goes a step further by including additional requirements on top of the 3 times pile diameter rule to enhance performance and constructability. Another important consideration, which is often overlooked, is the minimum edge distance from the pile to the edge of the pile cap. This dimension is critical for preventing edge shear failure and ensuring sufficient pile cap material at the edges for structural integrity. BS8110 design code recommends a minimum clear edge distance of 150 millimeters. Meanwhile, the CRSI Design Guide for Pile Caps provides more detailed recommendations, specifying center-to-edge distances for various pile working load capacities. These guidelines help tailor the design to the project's specific demands, ensuring both safety and efficiency. Now that we've covered the fundamental concepts and provisions, let's move on to a practical example. Here's the problem statement. A pile cap supports a 400 by 400 mm concentric column subjected to an axial dead load of 500 kN and a live load of 400 kN. Each pile with a diameter of 300 mm has a working capacity of 170 kN. The foundation should be designed with the following material properties: compressive strength of 28 MPa, steel yield strength of 300 MPa, and a reinforcement diameter of 20 mm. Let's break this down step by step to determine the required pile cap design. To determine the number of piles needed to support the load, divide the allowable load by the capacity of a single pile. There are a few ways to adjust the calculation for additional weights. One option is to add one pile to the initially calculated value. Another approach is to increase the required number of piles by a small percentage, such as 10%. Alternatively, if the additional weight is known, it can be subtracted directly from the working capacity to refine the result. By applying the first two options, we can determine the required number of piles. However, for this example, we'll use the add one pile approach. Next, we can calculate the pile dimensions by first selecting the most suitable pile layout. This layout must consider both the minimum spacing between piles and the minimum edge distance. In this example, we'll use a spacing of 3 times the pile diameter and a clear edge distance of 150 millimeters. Note that the final dimension can be increased depending on the other requirements, as we have just complied with the minimum requirements. For this example, we will retain the computed pile cap dimension. This is the 3D view of the pile cap and pile layout. Since there are no bending loads in this case, we can evenly distribute the ultimate load among all the piles. The ultimate reaction for each pile is simply the ultimate load combination divided by the total number of piles. To determine the rebar arrangement, we'll assume the lower layer of rebars runs along the x-axis as the pile cap is square. We can now check for punching shear. VU is calculated as the difference between PU and the reaction of a single pile. This value is then equated to the punching shear capacity, where the effective depth, D, is unknown. The parameter BO, which represents the perimeter of the punching area, is defined as 4 times the sum of D and the column width. To solve for D, we can use either trial and error or the quadratic formula. Since most calculators have a shift solve function, we'll use that for efficiency. The solution will yield 2 values, but we'll select only the positive one. Finally, we determine the pile cap thickness by adding the effective depth to the concrete cover and the diameter of the reinforcing bar. Next, we address beam shear, starting with the y-axis. After applying the section cut, 3 piles remain, meaning the ultimate shear is equal to 3 times the reaction of a single pile. This ultimate shear is then equated to the beam shear capacity, where the effective depth, D, is the unknown. Since the y-axis rebars are assumed to be upper layer bars, the pile cap thickness is calculated by adding the effective depth, the concrete cover, and 1.5 times the diameter of the reinforcement bar. We'll make a similar cut for the x-axis beam shear. This time only 2 piles remain. After solving for the effective depth, D, we calculate the pile cap thickness by adding D, the concrete cover, and half the bar diameter. With the 3 thicknesses determined, we select the largest value as the final pile cap thickness. Next, we compare this thickness with the minimum requirement specified in NSCP C101 2015, section 413.42. If the calculated thickness is less than the minimum, we will adopt the code prescribed value instead. Now let's move on to the flexure design. We begin by identifying the critical section cut, as shown. To compute the moment at this section, we multiply the reactions of the piles by their respective distances from the critical section. In this case, there are 2 pile reactions contributing to the moment after the section cut. Let's go through the flow of the calculation for the flexure design. While I won't delve into every detail here, as we've addressed similar examples before, I'll focus on key points. Specifically, the effective depth is calculated based on the assumption that the rebars along the x-axis are positioned in the lower layer. Moving on to the flexure design for the y-axis, we now have 3 pile reactions remaining after the critical section cut. Now, when performing the design, it is important to note that the effective depth is calculated with the assumption that the rebars along the y-axis are placed in the upper layer. In conclusion, the final step in the process is to complete the detailing of the pile cap. ensuring all reinforcements and specifications are properly laid out. That wraps up this video. If you found this content helpful, don't forget to like, share, and subscribe for more civil engineering tutorials. Thanks for watching, and I'll see you in the next one.